All right, so today's video will introduce our first topic for Unit 5. One thing to note is that you will not be allowed to use graphing calculators on the Unit 5 test. So if you want to have a calculator, you can use a scientific calculator or a Fourier function calculator. You will not be able to use the calculator on your cell phones at all. So you can get one of those if you would like, but you will not be able to use your graphing calculator on the test at all. So our first topic is maximum and minimum values of functions. And in this section, we're going to learn how to find those maximum and minimum values algebraically. So first, a definition. A function is said to have an absolute maximum if f of c is greater than or equal to f of x for all the x values in a domain. So what that's really saying is f of c is a specific y value. F of x is all the y values. So it's saying if there's some y value that a function takes on, and it's greater than or equal to every y value in the domain, then it must be an absolute maximum, saying it must be the largest one. So when we're talking maximums and minimums, we're talking the y values, because those are the values the function actually takes on. So they say f of c is your maximum, because f of c is the y value. And similarly, you can say it for the minimum by just flipping around the inequality. If f of c, some specific y value, is less than or equal to all y values, f of x, in your domain, then you can say that f of c is an absolute minimum. And we say absolute because it is the smallest y value, or if it's an absolute maximum, the largest y value in the entire domain. And here's just a visual of that. So in this picture, our absolute maximum would be located here. Now we would say our absolute maximum is located at D. So you say at whatever x value it is. And we would say the actual absolute maximum is f of D, whatever the y value is. So you say it's located at a certain x value, and the actual maximum or minimum value is the y value that it takes on there. Now our minimum, absolute minimum value would occur right here. So we would say our absolute minimum is at A, and the absolute minimum value is f of A, whatever that y value is. So overall, we have that a function has a local maximum, also referred to as a relative maximum, if a specific y value is greater than or equal to all the y values nearby it. So absolute, which we saw on the previous pages, was overall for the entire domain. We can also work with these local or relative maxes and mins, basically if it's the biggest thing of any y values close to it. And likewise, the same could be said for a minimum. If a certain y value is less than all the y values nearby it, we would call it a relative or local minimum. So one example, let's think about cosine. Cosine just repeats itself over and over and over again. So we say that cosine takes on a local maximum, and in this case it also happens to be an absolute maximum because it's the largest y value anywhere, each time it hits a y value of 1. And likewise, it hits a local minimum, and which also happens to be an absolute minimum every time it hits a y value of -1. So this just shows that absolute and local maxes and mins could occur more than once, potentially. So let's think of the graph of x squared. and think about its absolute and local maxes and mins. Well, hopefully we know the graph of x squared looks something like this. Where we have that minimum point. Well, at 0, 0, it is a local mat or local min because it is the y value smaller than y values around it. It also is an absolute min because it is the smallest y value in the entire domain. Now, because our function increases without bound, there are no maximums for this particular graph. Now here in x cubed, there is no local or absolute minimums. There is no local or absolute maximums. So that in all, there are no maxes or mins at all. There's no absolute min because there's no lowest y value. It goes down forever. And for the same reason, there's no absolute max. There's no locals because there's no y values that are either larger or smaller than all the y values around it. This function is increasing the whole time. Okay, here's another visual example of a graph. And what we're going to do from this graph on the domain -1 to 4, we're going to see if we can pick out what are the local maxes and mins and the absolute maxes and mins. Now, a couple things to keep in mind. A local or relative max or min cannot occur at an endpoint. The reason being, to be a local max or min, you need to be higher or lower than all of the points nearby it. If you're at an endpoint, we don't necessarily know what's on the other side, so therefore we cannot call it a local or relative max or min. So the local maxes and mins cannot occur at endpoints. Absolutes could possibly occur at endpoints because those are just the highest or lowest y value in the set domain. So our domain ends at those endpoints, so that's why that could be there. Now, things could be both local and absolute maxes or mins. It is possible to be both. So the first thing to notice is that at 1, 5, there is a local maximum. So we would say at 1, there is a local maximum of 5. The absolute maximum occurs at -1, and the absolute maximum is 37, we would say. Remember, your absolutes can occur at endpoints, locals cannot. Okay, that's why -1, 37 is not a local maximum because it's at an endpoint. And those are our only maximums that are taking place. Now for our minimums, take note that 0, 0 is a local minimum. So we would say at 0, the x value, there is a local minimum of 0, the y value. And at 3, -27, it is both a local and absolute minimum. Local because the y value is less than all the y values around it. Absolute because it is the smallest y value for the entire domain. So we would say at 3, there is a local minimum of -27, and at 3, there's also a absolute minimum of -27. Now, it's important to note at our endpoint there of 4, it is neither a local nor absolute maximum because it's not the absolute, it's not the highest overall, and your endpoints can't be local. So it's basically nothing. Now, this is an important definition you're going to want to know and have it memorized word for word. That's why it's starred so much. This is the extreme value theorem. If f is a continuous function, okay, meaning there's no jumps, breaks, things like that, places where it's undefined, on a closed interval AB, so meaning it includes the endpoint values, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers c and d in the closed interval AB. So in everyday language, this is saying if you have a continuous function on a closed interval, there must be some highest y value on the closed interval and some lowest y value on that closed interval. And this will be an important definition that we will use throughout the unit. So some visuals of the extreme value theorem. So here's some closed intervals AB. In the first picture there, notice we take on the absolute maximum at C on that closed interval, and we take on an absolute minimum at D. So the first case shows when those absolute maxes or mins may not occur at an endpoint, maybe somewhere inside the interval. The second example shows that they could potentially occur at an endpoint. They happen to show that the absolute min is occurring at an endpoint. It could potentially happen that the absolute max is at an endpoint as well. And then the third picture shows that those values could be attained more than once. You could basically have several spots that tie for the highest y value. So we have at C1 and C2, those both take on the absolute maximum, and then you have at D that takes on the absolute minimum. So the extreme value theorem just guarantees that it'll be taken on at least once in your closed interval for each the absolute maximum and absolute minimum. Here's some pictures to show you why it needs to be a continuous function. And if you don't have continuity, the theorem does not necessarily hold true. In the first example there, because of the open circle in that jump, the function never actually takes on a maximum value. It'll get closer and closer to 3 infinitely, but never hit 3. So if you give me any value closer to 3, I can just add a 9 on the end of that decimal and make it even higher. So it'll never attain an absolute maximum. Okay, but again, it was not continuous, so our theorem did not apply. And the right-hand picture, it's not a closed interval. It does not go to 2 and actually has an open circle at 0 as well. So on the left, it'll never reach a lowest value. It'll get closer and closer to 1 but never reach it. And on the right, it'll approach infinity, so it'll never take on an absolute max either. But again, it doesn't violate our theorem because it did not satisfy our 2 initial hypotheses. It has to be a closed interval and also has to be continuous. And here's just another picture with your local maximum and local minimums. Now note, at the local maximum and at the local minimum, we often will have horizontal tangent lines. When you have a horizontal tangent line, we know the value of our derivative is 0. This will play an important role in algebraically finding where those absolute maxes and mins occur. Or sorry, local maxes and mins occur. So another theorem, if a function has a local max or min at an x value, and the derivative exists, then that derivative must equal 0. So if there's a local max or min, and the derivative is going to exist there, then the derivative is going to equal 0. So in other words, it'll have a horizontal tangent line at that point. So the theorem has a few cautions in there that you can't just assume the local max or min will only be at the places where the derivative equals 0. And here's a couple reasons why. One, if we take the derivative of x cubed, we get 3x squared. It's pretty clear that 3x squared will equal 0 when you plug 0 in. But looking on the graph, you notice 0, 0 is neither a local max or local min. All that means is there's a horizontal tangent line there. So just because the derivative is equal to 0 at a point does not guarantee that there's a local max or min there. It is just a potential spot for a local max or min. Additionally, we can't assume that the places where the derivative is equal to 0 is the only places to look. We've seen ones like absolute value of x. Absolute value of x would have a local minimum when x is equal to 0. It's pretty clear to see that from the picture, but there's no horizontal tangent line there because the derivative actually does not exist. So we also need to caution and find the spots where the derivative might not exist. So example 5 just showed that just because the derivative equals 0, it's not necessarily a local max or min. And example 6 showed that there may be a local max or min where the derivative does not exist. So we need to keep those two things in mind. So putting those together, when looking for local maxes or mins, it would be logical the two places you should check are where the derivative is equal to 0 and where the derivative does not exist. We will refer to those places as critical numbers. So that's a vocab term you'll want to know. A critical number refers to an x value. It is the x values where the derivative is equal to 0 or where the derivative does not exist. So if a question says, find the critical values for the function, it needs to pop into your head, okay, I need to see where is the derivative not going to exist and where is the derivative going to equal 0. So here's a formal definition of that. Critical number of a function f is a number c, so c is an x value, in the domain of f such that either your derivative f prime of c is equal to 0 or your derivative f prime of c does not exist. So again, when we talk critical numbers, we are talking x values. So let's try an example. We're going to find the critical numbers in this function. Now we have x to the 3/5 times the quantity 4 minus x. To make our life easier when taking the derivative, before we take the derivative, it might make sense to distribute that x to the 3/5. Now keep in mind, this is x to the first, and because we'll have to add them eventually, it might be helpful to think of it as x to the 5/5. So we'll rewrite f of x as 4x to the 3/5 minus, this will give us x to the 8/5. Now we'll take our derivative, because the critical numbers, we need to know when will the derivative not exist, and when will the derivative be equal to 0. So the 3/5 times the 4, that'll give us 12/5 x to the negative 2/5 minus 8/5 x to the 3/5. Now, notice we have a negative exponent. That would really move to the denominator of a fraction. Therefore, we want to try and pull out that x to the negative 2/5 so that we can set the remaining part equal to 0. When we pull out an x to the negative 2/5, that'll leave us with 12/5 minus 8/5 times x raised to some power. Well, we need to think about x to the negative 2/5 times x to what power will give us 3/5. Well, together they would need to add to 3/5, so that means this must be 5/5, which is really just x to the first. So now we need to set each of these equal to 0. So this is really 1 over x to the 2/5 that we want to set equal to 0. Well, because you have 1 in the numerator, this fraction will never be 0. However, because we have x's in the denominator, we need to see what could possibly make it undefined, because those are values where the derivative won't exist. In this case, it would be when x is equal to 0. So x equals 0 would be a critical number. For the second part, 12 over 5 minus 8/5 x will set equal to 0. That'll give us negative 8/5 x equals 12/5. And when you divide, negative 12/5. When you divide by negative 8/5, you'll end up getting that x is 3/2. So our critical numbers we get when x is 3/2, because that's when the derivative would equal 0. And over on the left, nothing would make it 0, but x equals 0 would make it undefined, so that's a spot where the derivative would not exist. So critical numbers of 0 and 3/2. Another theorem, if a function has a local maximum or minimum at c, then we say that c is a critical number. Okay, just another way of saying what we said before. To find an absolute max or min, the places we should look are at the critical numbers and at the endpoints of the intervals. Because your critical numbers are where your local maxes and mins could occur, and the endpoints, while they're not locals, they could be the absolutes. So you always want to test your critical numbers and your endpoints to find the absolute maxes and mins. So what we'll do is when we're given a function, we want to find the absolute maxes and mins. We'll first find the critical numbers, just like we did in the example a second ago. Once we have those critical numbers, we'll take those and our endpoints and plug them into the function. Whichever one yields the largest y value, that y value will be our absolute max. Whichever one yields the smallest y value, that will be our absolute min. So let's see if we can do that in this case. Let's first find our critical values. We'll go ahead, take the derivative. F prime of x will be equal to 3x squared minus 6x. Because this is a polynomial, it will exist everywhere, so we don't get any critical numbers from spots the derivative doesn't exist. We've just got to set the derivative equal to 0. And when doing that, I'm going to go ahead and pull a 3x out, leaving us with x minus 2. Setting each part equal to 0, we'll get x equals 0, and x equals 2 is our two critical numbers. So we'll need to plug our critical numbers into our original function, and also we'll plug our endpoints of our interval. So f of negative 1/2 and f of 4. Now remember, the extreme value theorem guarantees that our function will take on an absolute max and an absolute min in this interval because it is continuous, it's a polynomial function, and it's on a closed interval. So when we plug in 0 to our original function, we get back 1. When we plug in 2, we get back negative 3. When we plug in negative 1/2, we get back 1/8. And when we plug in 4, we get back 17. So therefore, the negative 3 will be our absolute min. And the 17 will be our absolute max. So we would say an absolute min occurs of negative 3 occurs at 2. So negative 3 is the y value, 2 is the x value. We would say an absolute max of 17 occurs at 4. So if they ever ask, where does the absolute max occur, you would be giving the x value of where it occurs. If it asks what the absolute max is, you're giving the y value. And here's just a visual of that. There's our graph, our cubic. You can see your absolute min was at 2, negative 3, and your absolute max was at the end point there for 17. Now, if you have a graphing calculator, you can pretty easily find what the maxes and mins are. And if they're nice numbers, I mean, it does the same as doing it algebraically. But they might not always be nice numbers. So let's look at this case. Let's say we had f of x was equal to x minus 2 sine x going from 0 to 2 pi. So we had f of x was equal to x minus 2 sine x. And we wanted to go from 0 to 2 pi. And because it looks like our graph goes off the screen a little bit, we'll change our maximum value on our graph as well. So now we can see it. So notice we're going from 0 to 2 pi. To find this graphically on the calculator, we can do menu, analyze graph. We'll do the minimum first. Pick your lower bound, pick your upper bound, and notice the minimum pops up. It's occurring at 1.04 roughly, and the minimum value would be about negative 6.8 or negative 0.68. And we can do menu, analyze graph, maximum, do your left bound, do your right bound, and we get it's occurring at roughly 5.23, and the maximum value is about 6.96. Well, that's nice, but those are not exact values. Solving it algebraically can find us what the exact values are for those maxes and mins. So we know we need to test at the critical values and at the endpoints. So let's start out. Let's take our derivative. We'll get 1 minus 2 cos x. Since cos x has a domain of all real numbers, this will be defined everywhere, so there's no places where the derivative will not exist. We just need to know when will the derivative be equal to 0. Well, we can add our 2 cos x over, divide by 2, and we'll get cos x is equal to 1/2. It's easier usually to think in degrees, but remember we'll have to work in terms of radians, because all our derivative rules are in radians for trig functions. First off, cosine, using your ASTC, is positive in the first and the fourth. The special right triangle that has a 1 and a 2 in it is the 30, 60, 90. Square root of 3 being across from the 60, 1 across from the 30, and 2 across from the 90. That means a cos of a 60 had a cos of 60 gave us the 1/2. So that means we have a reference angle of 60 in each of these quadrants, meaning that we're dealing with 60 and 300. Switching those to radians, multiplying by pi over 180. Remember, when you switch to radians, you put whatever you want in the numerator. We want radians, so the pi goes in the numerator. This will give us pi over 3 and 5 pi over 3. So what this tells us, these are the x values that are our critical values. Those are the places where the derivative is equal to 0. So we need to test each of our critical values, f of pi over 3, f of 5 pi over 3. And then we also have to test our endpoints. Our endpoints were 0 and 2 pi. So we'll also test f of 0 and f of 2 pi. We'll see which one gives us the largest thing back, which one gives us the smallest thing back, and that'll tell us where our absolute max and absolute min is. Now keep in mind, our original function was f of x equal to x minus 2 sine x. So when we put pi over 3 in, we'll have pi over 3 minus 2 sine of pi over 3. Keep in mind, pi over 3 is like thinking 60. Sine of 60, looking at our special right triangle, is square root of 3 over 2. So this is really pi over 3 minus 2 times square root of 3 over 2, meaning we have pi over 3 minus square root of 3. And if you plug that in, that's roughly negative 0.68 or so. If we go to the 5 pi over 3, we'll put in 5 pi over 3 for x. So you'll have 5 pi over 3 minus 2 sine of 5 pi over 3. So that'll be 5 pi over 3 minus 2. Again, this is a reference angle of 60, so it's another square root of 3 over 2. But because it's in the fourth quadrant and we're now working with sine, it's got to be a negative. So it'll be times negative square root of 3 over 2. So we'll really end up with 5 pi over 3 plus square root of 3, which is approximately 6.96 or so. When we do 0, you'll have 0 minus 2 sine of 0. Well, since sine of 0 is 0, this whole thing is just 0. And then you'll have 2 pi minus 2 sine of 2 pi. Since sine of 2 pi is 0, we'll just get 2 pi back. And keep in mind, 2 pi is roughly 6.28 or so. So our largest value occurred at 5 pi over 3. So the exact value of that maximum would be 5 pi over 3 plus square root of 3. Our smallest value, the absolute min, would be the negative 1, which the exact value would be pi over 3 minus square root of 3. So as you can see, with calculus, we can find exactly what the maxes and mins are, where with the graphing calculator, it can just give you what the decimal approximation of that value is. And again, like we saw on the calculator graph page, there's our absolute min and our absolute maximum. That's all for today's video. We'll see you next class period.